Okay, so we're going to use these expressions for the derivatives. So let's go back to the expression that we had for the Lagrangian density. So this expression over here. And let's move this downstairs, okay? So we'll go there, let's make a copy, and we will just move this downstairs. Uh, and let's maybe make it red. Good. All right. So, uh, yeah, do that. We'll delete that. Let's move this. That's the Lagrangian density. Okay, good. So now notice something. I can rewrite this as follows. This is equal to, so I'm going to combine this d0 squared and this d3 squared. So we combine those by saying it is d0 phi plus d3 phi over the square root of 2 times by d0 phi minus d3 phi over the square root of 2. So the green terms above are equivalent to this green term below. So if you multiply those two out, it's the difference between two squares. Then we'll take minus 1/2 d1 phi squared minus 1/2 d2 phi squared minus 1/2 m squared phi squared. Now, the benefit of rewriting things in this way is that if we look at these two terms, well, d plus phi would be 1 over root 2 d naught phi plus d3 phi. So this first factor over here, we can now identify as d plus phi. And the second factor over here, which is the d naught phi minus d3 phi over square root of 2, is d minus phi. And then we've got minus 1/2 d1 phi squared minus 1/2 d2 phi squared, and then minus 1/2 m squared phi squared. Okay, so now we've gotten our Lagrangian in terms of d plus phi and d minus phi. So why is this useful? Okay, let's now swap to black. So this is our Lagrangian density that we are going to use now. The reason why this expression is useful is that if we calculate the conjugate momentum, so this will be a function of x plus, x minus, x1, and x2. Remember, the conjugate momentum is the derivative of the Lagrangian density, and usually we would have d phi dot, the time derivative of phi. But here, the thing that's playing the role of time is plus. So we're going to take dl d plus phi. And this will be at the same time x, and then x minus x1 and x2. And looking at the boxed formula just above, if we take a derivative with respect to d plus phi, we're going to get d minus phi. The only term that we're hitting is this first term in the Lagrangian. So we'll get d minus phi of x plus x minus x1 and x2. So this is the formula now for the conjugate momentum. Okay. First difference in being in the light cone frame. Well, second, we've also got a different foliation, but you can see that pi is d minus phi. Next, let's work out the equal x plus commutators. So what would the quantization condition be? So to quantize the theory, we would, as usual, impose an equal time commutator, and now time is x plus. So we'll impose an equal x plus commutator. So this is pi of x plus, x minus, x1, x2, and we'll calculate the commutator with phi at x plus. So this is equal x plus, that means equal time, and then we'll have y minus, y1, and y2. And what is this equal to? This will be minus I h bar will have a delta of x minus minus y minus, a delta of x1 minus y1, a delta of x2 minus y2. So this is the condition that you would impose to quantize this theory, and this is an equal x plus commutator. Okay, good. And finally, the last thing that I want to calculate is the Hamiltonian. So the Hamiltonian, as usual, would be an integral. And now it would be an integral over dx minus, an integral over dx1, and an integral over dx2 of the Hamiltonian density. And what is the Hamiltonian density? So let's put it over here. Now, I just want to remind you of what we'd usually write, okay? So this blue equation is just from the usual quantization. We would have a pi, we would have phi dot minus the Lagrangian. So this is the old formula. So let me just put old. So here, what would we have? We would have pi. Then we would have d plus phi, because remember, time is now being played by x plus, so phi dot is d plus phi, and it would be minus the Lagrangian. Okay, so if we look at the Lagrangian, there's the Lagrangian. It's got a d plus phi, d minus phi, and then a bunch of other terms. So now what will we have? D minus phi, d plus phi. Let me just write in the Lagrangian. I'm just going to write in that expression over here. So we'll have d plus phi, d minus phi, minus a half d1 phi squared, minus a half d2 phi squared, minus a half m squared phi squared. And what you can see immediately is that that first term over there cancels against that term over there. Then we've got a minus up front. Multiplying that in, we'll have a 1 half d1 phi squared plus 1 half d2 phi squared plus m squared over 2 phi squared. And that's the Hamiltonian density. Now, this is a pretty interesting formula, and at first sight, you may have been a little puzzled. So let me just record here the expression that we would usually have for the Hamiltonian density. We would have had 1 half pi squared plus 1 half gradient of phi dotted into the gradient of phi plus m squared over 2 phi squared. And what you notice is, this is an important thing, you notice that both pi and phi appear. Okay, look at the expression that we've got in the black box. Pi doesn't appear. Pi does, but pi doesn't. So you can see this light front quantization really looks genuinely different to an equal time quantization. Maybe just one more comment. So there's a few more things that I want to say, but let me just add in maybe one more comment that I remembered now, and I don't think I said this. I meant to, so let me say it now. When we talk about these equal x plus slices, if you had a ray of light moving towards the left, the ray of light would move along these lines. So these lines could be the paths that light would move along, but equivalently, you could have a wave, let's say that's the wave front, and the wave is moving towards the right, not towards the left. So the blue arrows would be single photons moving towards the left. This red line over here could be the front of some wave, and it progresses in this direction. At some later time, the front of the wave would be sitting over here. It just moves parallel to itself at the speed of light. So you can see on these equal x plus slices, we could also think that we are on the front of a null wave. So the front of a light wave. And that's also the origin of the name, or that's the origin of the name when we say light front quantization. Okay, so there are just a few more things that I want to discuss. We will continue in a moment.